All right, let's look into our intro on the different type of sequences and what sequences are. First, we will start with this do now. If you won a contest and you were given a choice of the following prizes, which one would you pick? Would you pick option 1, where you get $1,000 on the first day, $2,000 on the second day, $3,000 on the third day, and so on and so forth? And then you would wait until the 20 days are over to pick up your prize, like all of the money together. Or would you go with option 2, where you get $3 on the first day, $9 on the second day, $27 on the third day, and so on and so forth, until the 20 days when you pick up your money? So right off the bat, option 1 is going to sound better, because you're starting out with $1,000 the first day, where option 2, you're only getting $3 the first day. But it seems that option 2, the money is like getting quicker fast. It's going from 3 to 9 to 27 to 81. But of course, option 1 is still sounding better because it's 1,000, 2,000, 3,000, 4,000. So decide which option you would choose and think about why. Now let's think about the mathematical reason behind it. All right. If we just talk about 10 days, let's just talk about 10 days. 1 day, 2 day, 3 day, 4, 5, 6, 7, 8, 9, 10. Okay, and let's think about if you're adding 1,000. You would start with 1,000 the first day, 2,000 the second, then 3,000, 4,000, 5, 7,000, 8,000, 9,000, and 10,000. Okay, now the other option is when you start out with $3 the first day, $9 the second day, $27 the third day, $81 the fourth day. If you see the pattern, that's a pattern of us multiplying by 3. So let's continue. 81 times 3, that would give us 243. Let's do that times 3. That gives us 729. That times 3, that gives us 2,187. Then we get 6,561. That times 3 gets us 19,683. Ooh, the number's getting big quick. And then times that by 3, we get $59,049. Wow. So if we look on the 10th day, this is definitely a lot more money times like 6 of the first option. Let me add up all the money they got in the first option. They got $1,000. And they got 2,000, 3, 4,000, 5, 6, 7, 8, 9,000, and then they got 10,000. So in the 10 days using option 1, they would get 55,000 total. In option 2, where they're multiplying by 3, by the last day, they're already getting $59,000. So with option 2, you're already getting more money on the last day than you got in all the days combined of option 1. So I'm going to say option 2 is better. And did anything surprise me? Yes. How quickly option 2 added up. Well, multiplied, but yeah. Also, what surprised me is how I can make the same amount on day 10 with option 2 as actually more than I make in all of the days of option 1. All right, now next question. Now write a linear equation in standard form. Linear equation, that's when we have the y equals mx plus b. Remember, linear means something's being added. In standard form for the first option. Let y stand for the amount of money. So the amount of money is y equals, and x stand for the number of days. Okay, how much money do we start with? On day 0, we start with $0. So I don't need to add any money. But my slope, my rate of change is the $1,000. It's being added by each day for x amount of days. Now the next question says, now write an equation for the second option. Is it a linear expression? How will this equation be different from the equation for the first option? Well, it's not going to be linear because we're not adding something, so we need to multiply. Let's see if we're multiplying by 3. Well, 3 times 1, that gets me 3. 3 times 2, that gets me the 9. 3 times 3. Oh, no, that does not give me the 9. And the 3 times 3 does not give me the 27, so that's not going to work. I can't just do y equals 3x, because that would be me adding 3 every time. Let me see if I do an exponent. 3 raised to the first power, does that get me 3? It does. 3 raised to the second power, it gets me 9. 3 to the third power, that is 27. So it is an exponential function. 3 to the x power. It's exponential. That's how we show that we're multiplying by 3 every time. Alrighty. So both of those different options had to do with a different type of sequence. The one where you were adding had to do with what's called an arithmetic sequence, and the one where you were multiplying had to do with a geometric sequence. And that is what we are going to learn about now. So, intro to sequence. A sequence is a special type of function. It is a list of numbers called terms which are written and ordered with some type of pattern. So a sequence is a function whose set of inputs, the domain, is a subset of natural numbers, meaning you have the first term, second term, third term, fourth term. A sequence is often showed as an ordered list of numbers, and each number is called a term or an element. Sequence function notation can be a little tricky. We'll learn about that. So let's think about this domino example. It says, Marco is building towers out of dominoes. He uses a pattern to determine the number of dominoes to use at each building level, as shown. Use the illustration tower to answer the following questions. All right. Complete the table for levels 1 through 3. Let's do this. So level 1 would be 1, 2, 3, 4. 4 dominoes. Level 2, 1, 2, 3, 4, 5, 6, 7. Level 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So that's me completing the table. Now, question B. Determine the pattern Marco is using to determine the number of dominoes needed at each level. To get from 4 to 7, he's adding 3. To get from 7 to 10, he's adding 3. Because each time he's adding on this next level, which each level, you need the top and the 2 sides, but you don't need to put another base because you're already reusing the same base. So the pattern was adding 3. And now, complete the table for level 4 and sketch the tower Mark should build. Well, let's do the original one that's already there. And then every time he's just adding 1 tower. So it would be 13. Good. All right, let's look at these follow-up questions. The number of dominoes at each level forms a sequence or an ordered list of numbers. So our ordered list of numbers were 4, 7, 10, and 11. 13, I meant. Each number in the sequence is called a term. So each number of dominoes, we call that a term. The nth term in a sequence can be written using either. The nth term means the any number term. So like if we want to find, let's just say the 10th term, but we don't know we want to find the 10th term, we could just call it the nth term. That's whatever term is unknown. And we could write this using subscript notation or using function notation. And let's look at what these look like. Subscript notation. A subscript is a little number that's at the bottom. It's like the opposite of an exponent. It's not a little number at top, but it's a little number at the bottom. So if we have an means our sequence is called A, and n is the number term we don't know. So an is the term. N is the term number, and we put the n like small. Then the other notation we could use is function notation. This one we're used to. Let's say our sequence is called f, and then in parentheses we put the nth term, which we don't know, which is n. All right. So, using the domino example, answer the following questions. What are the first 3 terms in the sequence? Well, the first term, the level 1, was 4. The second term, level 2, was 7. And the third term was 10. And what was the value of A4? It doesn't matter if you wrote it as A4 like this or if you wrote it at A4 like this. Those both mean the same thing. And in the 4th level, there was 13 dominoes. And now it says, without sketching a model, could you find A5? Explain. Yes, you take a 4, which equals 10, no, 13 on it, and you add 3, which is 16. Good. All right. Now, let's have an intro into arithmetic sequences. An arithmetic sequence is a type of sequence that follows a pattern of adding, just like how before we were adding 3. It's a sequence where the difference between consecutive terms is consistent. So to see how each number differs, like in the number of dominoes one, we went from 4 to 7. That differed by 3 numbers. Then 7 to 10, that differed by 3 numbers. 10 to 13 differed by 3 numbers. And then this constant difference between terms, we call it a common difference. We can identify if a sequence is arithmetic by calculating. We take the second term and subtract it from the first, see what that number is. Then we take the third number and subtract it by the second, see what that number is. If they are equal, then most likely it's an arithmetic sequence. But if you want to double check one more time, you could do the fourth term minus the third term and just make sure that equals the same common difference. Essentially, we are looking to see if the sequence follows a pattern of adding the same number. Sometimes your numbers will go up, and that means that you're adding a positive number, but if your numbers are going down, that means you're adding a negative number. And this is how we go from one term to the next. All right, let's look at this Regents questions. Which sequence is arithmetic? All right, to get from 5 to 10, we add 5. To get from 10 to 20, we add 10. 20 to 40, we add 20. Well, that's not a common difference because the numbers that it's changed by is not common, so it's not A. Let's look at the next one. To get from 100 to 50, we would add negative 50. If you don't notice, you could take the second term, which is 50, and subtract it from the first term, which is 100. Now, how do we get from 50 to 25? We would be adding negative 25. So no, this is not arithmetic because we are not adding the same number. All right, let's look at the next one. To get from 20 to 13, so let's do 13 minus 20. The number's going down, so it should be negative. That's us adding negative 7. Okay? Then to get from 6 to 13, again, that's us adding negative 7. So yes, this is our answer because we are adding the same number. All right, let's look at the next question. In a sequence, the first term is 4. So term 1 is 4. The common difference is 3, and they want us to find the fifth term. So all we got to do is add 3. 4 plus 3 is 7. 7 plus 3 is 10. 10 plus 3 is 13. And 13 plus 3 is 16. We should have instantly known that our answer was not going to be our 11, and our answer was not going to be negative 8, because if our common difference is a positive number, then we have to be higher than whatever our first term was. All right, let's look at the next question. Let's practice. Determine if each sequence below is arithmetic. If so, record the common difference. All right, sequence A. To get from 3 to 5, we add 2. 5 to 7, add 2. So yes, it is. And our common difference, D, equals 2. We were adding 2. All right, let's look at the next one. From 50 to 42. 42 minus 50. That would be, we're adding negative 8. 34 minus 42. 8, we're adding negative 8. So yes. And what is the common difference? Negative 8. Let's look at the next one. To get from 3 to 6, that means we're adding 3. 6 to 12, we're adding 6. So no, which means there's not a common difference. All right, the next one. To get from 15 to 20, we're adding 5. 20 to 15, we're doing plus negative 5. So no, because there is not a common difference. Going up and going down does not make sense. All right, the next one. 27 minus 31. That means we were adding negative 4. Then 23 minus 27. That means we were adding negative 4. So yes, And the common difference would be -4. All right, let's look at the next question. This is an example of a yoga question. Now in Zen, a new yoga studio offers a membership as an incentive if they refer a friend within a week of joining the studio. The table below shows the total number of studio memberships based on the number of weeks since opening. What pattern do I notice in the terms? Well, here every week it went up by 1 week, and now let's look at the members. To get from 6 to 12, we added 6 people. 12 to 24, we added 12 people. 24 to 48, we added 24 people. So this is not going to be an arithmetic sequence because we did not add by the same amount. But to get from 6 to 12, we multiplied 2. 12 to 24, we multiplied 2. 24 to 48, we multiplied 2. So what's the pattern? Multiply by 2. All right. If the pattern continues, how many members would you expect in week 5? Well, let's multiply by 2 again. 48 times 2, that is 96. So week 5, 96 members. Is this an example of an arithmetic sequence? No, because we are not adding the same amount. There's no common difference. All right, let's look at this next question. Intro to geometric sequences. The list of members represents a geometric sequence which is described below. A geometric sequence is a sequence where the ratio between the consecutive terms is constant. The number that you multiply from one term to the next, that's a ratio. This constant ratio between terms is called the common ratio. We could identify if a sequence is geometric by first, just find out that it's not arithmetic, you didn't add the same amount. And then we could do the second term divided by the first term, the third term divided by the second, the fourth term divided by the third, and so on and so forth. You always divide the previous term by the further term by the previous term. And we see if we end up with the same common ratio. Essentially, we are looking to see if the sequence follows a pattern of multiplying the same number. The number that gets multiplied is called the common ratio. If your sequence is going up, the values of the numbers are going up, that means you're multiplying by a whole number. If not a whole number, a number that's greater than 1. But if your sequence is going down, the numbers are decreasing, that means you're multiplying by a decimal or a fraction that's smaller than 1. All right. So let's practice. For each geometric sequence in 1 through 3, determine the common ratio in the next term. All right. How do we get from 2 to 8? We multiply by 4. 8 to 32, we multiply by 4. So our common ratio is 4. And now let's see, what is 128 times 4? That is 512. All right, next question. 128 to 64. I'm not sure off the top of my head, so let me do 64 divided by 128. That gets me a half. Let's do 32 divided by 64, a half. So my common ratio is 1/2, or you could write 0.5. And let's get to the next one. 8 times 0.5, that gets me 4. So my sixth term would be 4. All right, and the next question, how do we get from -1 to 5? 5 divided by -1 gets me -5. -25 divided by 5 gets me -5. So the number I'm multiplying by is -5. So let's do -25 times -5, and we get 125. If you could see, we start out with a negative number, then a negative, and then it goes positive and positive, because when you multiply by negative, it changes the sign. All right. Jane wrote a geometric sequence where A1 equals 2 and the common ratio is 5. So our first term is 2, and then I know we're going to multiply by 5. List the first 4 terms. So second term, third term, and fourth term. How do we find it? We're going to multiply by 5. 2 times 5 is 10. 10 times 5 is 50. 50 times 5 is 250. we multiplied each previous term by 5. Good. All right, let's look at the next question. Consider the following patterns. Which pattern is geometric? All right, let's look at the first one. Take the first number, 12.9, and divide it by 16. Okay, now let's do the third number, 9, divided by the second number, 12.9. That is not the same, so it's not going to be choice 1. Let's look at 2. Take the second number, which is 4, and divide it by 1. Then take the third number and divide it by the second. That is not the same pattern. Number 3. Take the second number and divide it by the first. Then take the third number and divide it by the second. And that is not the same pattern. So I think it has to be 4, but I like to double check my answers before I commit. So let's do the second fraction, 2 over 3, divided by the first, which is 1 over 2. And we get 4 over 3. Now let's take the third number, which is 3 over 4, and let's divide it by the second, which is 2 over 3, and we get, did I type the name wrong? Huh. Why is none of these becoming geometric? Oh my goodness. I messed up the first one. Because I thought this was saying 12.9. There's two different numbers. My bad. See, that's why it's good to always check the last one to make sure we didn't make a mistake. Once I seen the last one doesn't work, I was like, huh? So let's try this again. For the first one, let's do negative 12 divided by 16. Then let's do this third number, 9, divided by negative 12. And we get the same common ratio. Good thing we double checked. I'm very happy. That was good for you guys to see that. Sometimes we all make mistakes, but you want to check all the answer choices just to make sure that you are sure that the rest are wrong and yours is right. Alrighty. Another questions. In a sequence, the first term is 4, and the common ratio is 3. The fifth term is, let's see. The fifth term is question mark. Oh, I meant to say that this is our first term. This is our first term down here, which the first term is 4. And I said our common ratio is 3, so that means we're multiplying by 3. 4 times 3 is 12. 12 times 3 is 36. 36 times 3 is 108. And 108 times 3 is 324, which is the last answer choice. Nice job. All right, let's look at the next question. This is going to be our little wrap-up. Summarize the difference between arithmetic and geometric sequences by listing their characteristics. All right, the first one, you have to add a number, where with geometric, you multiply. All right. With this one, you have a common difference, where here, you have a common ratio. And if you compare this to anything we know, an arithmetic sequence is an example of linear. Linear is also the type of function where you add, where geometric would be an example of exponential, where you multiply. Alrighty, and that wraps up our lesson on an intro to sequences and the difference between the two.